Welcome to this explainer. Look, if you're an ops or supply chain leader, I know material costs are constantly top of mind for you. It's the name of the game, right? Well, today we're taking this foundational mathematical concept and really turning it into a practical executive playbook for cost management. Let's dive right in and look at how you can optimize material costs using a super effective yet honestly massively underutilized mathematical rule.
So, ask yourself, are your teams actually using the right math to optimize mixing costs? In the incredibly fast-paced world of manufacturing, commodities, or processing, literally a fraction of a percent in your material mixing can translate to huge swings in your profit margins. If your floor managers are out there relying on guesswork or, just basic, simple averages to blend materials, you're almost certainly leaving margin on the table.
All right, so here is what's on the agenda for us today. We'll look at cost optimization through allocation, the price mixing rule, managing liquid replacement operations, adjusting mixture concentrations, and we'll wrap up with some actionable implementation steps for your teams. We're covering the whole shebang, from basic inventory to complex continuous replacement.
Okay, kicking things off with Section 1, Cost Optimization through Allocation. We're going to start by taking what is essentially a textbook math concept and transforming it into a vital, strategic tool for your day-to-day cost management.
Let's start with a quick definition. Allocation is basically a mathematical rule used to find the exact ratio you need when mixing ingredients of different prices or different concentrations to hit a specific target mean. Think of this as your precision scalpel. Whether your operations are blending agricultural commodities like rice or tea, or mixing liquids of varying concentrations, or even, honestly, managing investments with different interest rates, this is the rule that dictates optimal efficiency.
And it gives us this really powerful, surprisingly simple mnemonic. Cheaper quantity to dearer quantity equals D minus M to M minus C. Or, to put it even more plainly, dearer minus mean to mean minus cheaper. This one single formula is literally the engine behind optimal mixing. Your mean is just your target price or concentration. You subtract that mean from your expensive or dearer ingredient, and you subtract your cheaper ingredient from the mean. It's a simple cross-subtraction method that instantly spits out the perfect ratio.
Let's move right along to Section 2, the price mixing rule. Let's see how this all builds into standard inventory pricing scenarios.
Okay, let's look at a really practical example straight from our source material. Imagine your operation mixes tea. You've got this cheaper inventory, let's call it C, costing 60 rupees per kilogram, and you have a dearer, more expensive inventory, D, costing 90 rupees a kilo. Now your target mean, the value you actually want that final blend to hit, is 75 rupees per kilo. To calculate this, we just take that dearer price of 90 minus the mean of 75, which gives us 15. Then, we take the mean of 75 minus the cheaper price of 60, which also gives us 15. And boom, that cross-subtraction gives us a perfect 1-to-1 ratio. This reveals the absolute optimal blend to balance your costs and hit that desired inventory value. So for every single kilogram of the 60 rupee tea, you mix exactly 1 kilogram of the 90 rupee tea to hit a perfect 75 rupee blend. It completely 100% removes the guesswork from your inventory valuation.
Next up, we are shifting gears from static mixing to something way more dynamic. Welcome to Section 3, Managing Liquid Replacement Operations. This is where things can get pretty complex on the floor, especially when you're dealing with continuous removal and replacement in liquid processing. Now, when you're managing continuous removal and replacement, this is the exact formula your engineers need to be using. Final quantity equals the initial quantity times 1 minus the removed volume divided by the total volume, all raised to the power of n. This is specifically built for those operations where a set amount of liquid is repeatedly taken out of a vat or a tank and then replaced by pure water, or whatever base liquid you use, over and over again. And here is a super common trap. People often think that removing and replacing liquids reduces that original component linearly. But actually, scratch that. It absolutely does not. True removal and replacement reduces the original component exponentially. That little to the power of n in our formula, that's doing the heavy lifting there. If your leadership team doesn't ensure the floor understands this exponential reduction, your quality control and your cost projections are going to be wildly off base. Moving right along, let's tackle quality and precision in Section 4, Adjusting Mixture Concentrations.
So, we're analyzing a scenario here where we have a 40-liter mixture of milk and water, and it's currently sitting at a 3-to-2 ratio. We need to shift that to a 3-to-5 ratio. To pull this off, we have to add pure water. The source breaks down the logic here brilliantly. Instead of juggling total volumes right from the start, we calculate the alligation based on the water percentage specifically. So our initial water concentration is 40% because 16 liters out of the 40 is water. The pure water we're adding, that has 100% concentration. Our target final water concentration, based on that new 3:5 ratio, means water makes up 5 parts out of 8 total, which is exactly 62.5%. By applying the alligation rule to these percentages, subtracting that 62.5 target from 100 and subtracting the 40 from 62.5, we get our exact operational efficiency metric, 24 liters. Literally, by adding exactly 24 liters of pure water, you hit your target concentration flawlessly. No overpouring, no wasting expensive product, just absolute mathematical precision dictating your entire operation. Okay, so how do we actually make this standard practice? Let's turn to Section 5, Implementation Steps for Teams. It's time to turn these abstract formulas into a real, actionable playbook for your operational teams.
Here are 3 simple, basically foolproof steps for applying the price mixing rule correctly out on the floor. Step 1, identify your cheaper and dearer components, whether you're looking at price or concentration. Step 2, clearly define the exact target mean value you are aiming for. And Step 3, apply that alligation rule, dearer minus mean to mean minus cheaper, to find your perfect ratio. It's a highly standardized workflow that just leaves zero room for error.
But as an executive, you need to know exactly where your margins are bleeding due to floor-level mistakes. First up, confusing the cheaper and dearer components. Teams should always double-check that the cheaper one is indeed the lower price or concentration. Second, and honestly this is a massive operational risk, using simple averages when alligation is actually required. Teams so often ruin margins by mistakenly relying on a simple average for an intermediate value, rather than properly weighting it with alligation. And third, just like we talked about earlier, mistakenly assuming replacement operations reduce components linearly instead of exponentially.
So if you take away just one thing, the absolutely crucial point here is this single overarching formula, the golden rule. Alligation equals dear minus mean to mean minus cheaper. It governs pricing, it governs concentrations, and it scales effortlessly across all your operational needs. It works for percentages, speeds, interest rates, virtually any scenario where you're blending 2 values into a target mean.
Which leaves us with this final, kind of provocative thought. Are your operational teams relying on simple averages when allocation could literally be saving you money? It's a really critical question for any leader looking to optimize efficiency and tighten up that bottom line. So take a look at your floor operations this week, ask around, and see if the golden rule is actually being applied. Thanks for joining me for this explainer, and I really hope this playbook helps you go out there and unlock some new margins in your operations.